Okay. A function. A function f is said to be continuous. Boys and girls, yes. We will record tomorrow because we gotta get through this. I promise. The limit as x approaches a of f of x is equal to f of a. Continuity is not the most difficult concept to master, but it is one of the pieces that you're going to have to know for your next test. So we just got done with the precise definition of a limit. We'll do our SON tomorrow. I thought we'd get going on Monday with this right away. But there's really three pieces that it has to satisfy, and you do have to know these three, okay? So the first criteria that has to be satisfied, make sure I'm in the same order as your book, is this. F of A is defined. So A exists in the domain of F. So, for example, a period and then a little letter a because I can't begin with a capital because it is a small a. So, yeah, something happened to the board. I don't know. I think I hit it too hard. So, it's kind of what happens sometimes. So, another row of lights. Yeah, we'll give that a shot. Dylan Sprague kid. He never does go to class, does he? He's always out in the hallway. F of A is defined. A exists in the domain of F. So, for example, let me just give you one example. Suppose I had the function 1 over x. At what value is 1 over x not defined? 0. So, therefore, f of x would not be continuous at 0. Okay, so it has to be defined. Does that make sense? Okay, here's another thing that must be true. The limit as x approaches a of f of x must exist. So again, if you consider that function, which we said was 1 over x, you maybe realize that the graph looks like this. First of all, is it defined at 0? No, it is not. You know, f of 0 does not exist. Second of all, does the limit as x approaches 0 exist? No, because from the left hand you get negative infinity, and from the positive you get positive infinity. So therefore, the limit does not exist. So already, 1 over x is not continuous at 0. It fails the first one. It also fails the second one. But the third one is very crucial, and it has to be this. So for example, the limit as x approaches a of f of x must equal f of a. And that's the trickiest part that we're going to have to help you understand and define. Okay. So, example 1 says, using the graph at the right, identify the numbers for which f of x is discontinuous. Identify which of the three requirements it fails to meet. And finally, identify the intervals for which f of x is continuous. Okay? Let's just start off with the basic piece here, and then we'll get to the intervals later on. First of all, is f of x continuous at -5? No, it is not. Okay? So it says identify the numbers for which f of x is discontinuous. So I'm going to write discontinuous. At x equals 5. Okay, so, and then we need to state the requirements. It fails, oh, I'm sorry, -5. Thank you. I'm going to state the requirement that it fails to meet. So I start with the first one. If I plug in -5, do I get an output? What is the output? 3. So, does it meet the first requirement? Yeah. There's a value. If I plug in -5, I get an output. Okay? Now, let's look at the second one. What is the limit as x approaches -5? Yeah, 7. So, for example, I could say f of -5 is equal to 3. I could say the limit as x approaches negative 5 is equal to 7. The third requirement says, are those two the same? No, they're not the same. So because the limit as x approaches negative 5 and because the value at negative 5 are not the same, the limit does not exist. Or I'm sorry, it is discontinuous. So it fails because of the third criteria. So just as identify which of the three requirements it fails to meet, it fails the third one. Okay? So therefore we can be done with this one. Now, the very informal way of expressing continuity is this. If you could draw the shape without picking up your pencil, then it's continuous. If you have to pick up your pencil, which I do to put that point there, then it's discontinuous. So our next point of discontinuity would be at x equals 1. So let's try the first test. I see does f of 1 exist? Does it? Yeah, what is f of 1? 6. Does the limit exist as x approaches 1? Well, why? Right, because the left is not the right. If I approach it from the left, I have negative 3. If I approach it from the right, I have positive 1. Those are not the same. So the limit as x approaches 1 does not exist. Therefore, it fails number 2. And finally, let's look at this last part here. It also, x equals 4 is problematic as well. The first one, does f of 4 exist? No. So if you write f of 4, you could just say does not exist. So it fails to meet because of the very first requirement. These are requirements that you have to, memorize. You have to know these for the test. And that's all there is. You have to be able to plug it in and get a value, so it's got to be within the domain. The limit has to exist, and then those two have to be the same. So you really only need to memorize 2 of them, okay? Because they have to be equal to each other. Question? Oh, good. So the first question was, how did I pick x equals negative 5, x equals 1, and x equals 4? As you can see from your graph, that's where I have discontinuities. That's where if I'm drawing the graph, I would be picking up my pencil. Okay? All right? Any questions before we move on? That's as difficult as it gets. Well, maybe not. We'll see. All right. It says, use the definition of continuity and the properties of limits to show that the function is continuous at the given number. So, in order to show it's continuous, I must do the first part, which is show what? F of 2 exists. It says I want to show that the function is continuous at the single point of a equals 2. So, does f of 2 exist? What do I get? I get 1. Second of all, I have to show that the limit exists. The limit as x approaches 2 of 2x minus 3. Now, I'm not going to make you do this. But technically, what would we do here? We would do the precise definition of a limit and prove this, right? But no, that's going to be a waste of our time. Well, I should say waste. I mean, that's kind of a harsh word. It would be more than we really needed to do. So we learned that in order to evaluate a limit like this, you could simply plug it in, right? And so the limit is equal to 1. And the third thing I would say, so this is really just practice of stating these things. The third thing I would say is that f of 2, I'm sorry. The limit as x approaches 2 of f of 2 excuse me, 2x minus 3 is equal to f of 2, which is 1. So I just said that number 2 is the same as number 1, which is equal to 1. So that's all I did. So I've said my three pieces. It's defined at that spot, which is 1. The limit exists. And the third part, I have that. Okay, let's do the next one. Okay, what is g of 1? Negative 1. What is the limit as x approaches 1 of 1 over x minus 2? Negative 1. And so I can then say that the limit as x approaches 1 of 1 over x minus 2 is the same as g of 1, which is equal to, in these cases, negative 1. That's all there is to it. Those are the requirements for continuity. Any questions on those two? Can you memorize those three pieces? Good. Let's flip over. Did Laura say no? Laura Piper. I'm surprised. Okay. It says explain why the function is discontinuous at the given number a. Sketch a graph of the function. So let's sketch a graph. Take out your calculators. I know you guys love this part. I have a rational function, namely x squared minus 4 minus 4. Thank you, Ben. What would I do without you? X squared minus 4 divided by x minus 2. Zoom standard, so zoom 6. So as I look at that, what does it look like? Is that surprising to you? No, because you've learned about this type of function before. You actually said that x minus 2 times x plus 2 divided by x minus 2, we would cancel those out, so it's going to look just like x plus 2, only what do we know we have extra to this line? Yeah, it's undefined at the value of 2. So we have this hole. If you put a, the value of 2, so 1, 2, if you put that into your function, it's undefined at that spot. So this graph looks like a line, but there's an undefined value of it at technically the coordinate 2, 4. How do I get 2, 4? Well, it says 2, and if you plug it into x plus 2, you get 4 as your y value. So I know that that's a problem. So if you were to, first of all, is this continuous? No. Which one of the three does it fail? It fails 1. It fails 1 right away. So, and we would say that f of, we would give the reason that simply f of 2 does not exist. Can't plug it in. Okay, let's look at B. What do you call B? Starts with a P. Piecewise function. Very good, Johnny Baringa. All right, so this one says x plus 1 for x less than 0. All right, so x less than 0, so back this way. Remember, we need to kind of define where we're at in terms of our y values. If I plug in 0, what do I get? I get 1. So we have an open circle at that spot, and we know that our line is going to look something like this. So that's that part of the graph. Now I'll do the other part of the graph. If we plug 0 into the square root of x, what do we get? 0. And it says that it's equal there, so I can have a closed circle there. and the graph goes that way. So that's why we practiced graphing piecewise functions earlier. I know you're excellent at that, which I'm very, very happy about. So now we need to first do the first test. Does it pass the first test? Why? F of 0 is equal to 0. So that's good to go. It's obvious it's discontinuous, right? Well, the second answer, does the limit exist? No. Why not? Because it's not the same as the right from the left. I'm very proud you guys are getting that. Last year really had a difficult idea stating that, but that's the definition. Left has to be the same as the right. So the limit from this side is positive 1. The limit from this side is 0. And so, I mean, you could actually write that out, but we'll just do the shorthand. We'll say the limit as x approaches 0 of the function does not exist. So therefore, it fails because of criteria 2. Question, Chrissy. All right, that was that's funny. Everybody laughed. Just kidding. Okay. All right, and now we have a last one, which is example 4. It says the following functions have a removable discontinuity for a point A. A removable discontinuity. Fill the discontinuity by writing a piecewise function. Okay, so we're going to sketch a graph and we're going to write a new function. All right, so let's draw a little graph. Now, A for the day, does anybody know what x squared minus 9 over x plus 3 is going to look like? Very good. It's going to look like the graph x minus 3, right? Because you can, do the x minus 3 times the x plus 3, divide by x plus 3. You see that those are going to cancel, and you're going to get that type of a graph. So I'm going to draw that, except there's a hole at... And how far down would that be? 0, or negative 3 and down how many? 6. How did you get negative 6? Yeah, you did negative 3 minus 3. So here's what we have. We have this type of a graph. Okay. And that's exactly what the function looks like. Now your calculator, because of the how it's pixelated, is going to have a difficult time actually getting that hole to exist in there. There's a way to do it, but it's really not that important. As long as you understand that's the case, and then we're good to go. So again, it says the following functions have a removable discontinuity for a point A, which is right here. Fill the discontinuity by writing a piecewise function. So I'm just going to fill that spot. So I'm going to say that f of x is equal to my original function, which is x squared minus 9 over x plus 3 for values x what? Even more than that. Not just greater than, but also less than. Anything so long as it's not equal to. So as long as x doesn't equal negative 3, that's what my function is. Like this? Okay. So f of x is going to be x squared minus 9 over x plus 3 for values x not equal to negative 3. But now I have to fill the discontinuity by putting negative 3 back into my function. And if x is going to be equal to negative 3 at a certain spot, in order to make it continuous, what value should I put in there? Negative 6. So I just filled that spot. At negative 3, the function is equal to negative 6. It's now continuous from negative infinity to positive infinity. I filled the discontinuity. And that's that. We do one more. We made it through the entire notes. Holy cow. We're on a roll. Well, it's just, it's Monday. You guys had homecoming. Well, yeah, but you're going to have tomorrow to work on it, Yeah, I'd be fine with you guys taking some time to work tomorrow. You can ask questions about the previous day. I might get started on section 2.6 a little bit at the end, but yeah, so class will be a little bit shorter, and we have to record our song tomorrow anyways, so. How about this graph? Difference in two cubes. Thank you, Chrissy Munson. Oh, I have them. I'll hand them out. Thank you. X to the third minus 1 over x minus 1. We know that this factors 2, x minus 1 times x squared plus x plus 1 all over x minus 1. Very good, Jalen. You are on fire. X minus 1s will cancel, so this graph really looks like what? A parabola. That's what the graph looks like. Okay. Let's draw the graph of this parabola, okay? What is the y-intercept of this parabola? Positive 1. We know that much. Let's figure out the vertex. The vertex is negative b divided by 2a, so negative 1 divided by 2 times 1. So negative 1/2 will be the x value of the vertex. How do I figure out the y value? Plug it in. Negative 1/2 squared is 1/4 plus x is negative 1/2 plus 1. So you have 1/4 minus 1/2 is negative 1/4 plus 1 is 3/4. So negative 1/2 and positive 3/4 is going to be our vertex. So 1/2, maybe 1/2 and positive 3/4. So something about like that. So there we go. There's our graph. Whoop, I went over a full unit. My bad. Sorry. So negative 1/2, positive 3/4, so something like that. There we go. Now, it says a equals 1. Tell me, what is the y value going to be at a equals 1? Okay, we'll back up 1 second. Greta, first, in order to find the vertex of a parabola, I do negative b divided by 2a. So negative positive 1 divided by 2 times 1 is negative 1/2. Then I plug in the negative 1/2 into the function, and I get positive 3/4. That's my vertex. And now what I'm trying to find is it says that there is a discontinuity at a equals 1. Well, if I plugged in 1 to this, I would get what? 3. So over 1 and up 1, 2, 3. This is where I have a hole in the function. This one? Well, I just use the axis of symmetry to plot the other point on the other side, right? Parabolas are symmetrical. This is all stuff we should remember. Okay. So that's what the graph looks like. It's a parabola where the vertex is over at negative 1/2 and positive 3/4, and there is a hole that is at 1, 3. So if you wanted to write a piecewise function that would fill the discontinuity, you would write f of x is equal to what? X cubed minus 1 over x minus 1 for x values not equal to 1. However, in order to fill the discontinuity, I will say we will put 1 back into the domain, and you get 3. TJ, on fire. We filled the discontinuity. Well, that's exactly what we were told to do. It says fill the discontinuity. So that's what we did. It wasn't there. We modified the function. They asked us to do it, so we said, we were consultants. They paid us $80 an hour. We said, all right, we make the big money. We'll do whatever you ask us to. All right, I'm going to pause it, and I have some things to hand out as well as, you guys can see your assignment. Okay, in case anybody's watching, Rebecca or somebody, 2.5. You can see section 2.5. This is continuity. You're going to do problems 3, 4, 10 through 12, 15 through 19, and 41A and C, and that would be page 110.